great pleasure to introduce the keynote from Paolo Tonella. He's currently full professor at the Faculty of Informatics at the Software Institute, University of Svizzera Italiana in Lugano. If you look backward, he has been known for a lot of school research from Fondazione Bruno Kemmer in Trento, Italy, and he has been the recipient of important research in software testing. Look backward, we have the most influential paper on web-based testing for in ICSE, and very recently in SBST, the National Conference on Software Testing, and he is been also recently granted for the IRC starting advanced grant, one of the most prestigious grants as a main applicant. He's been doing a lot of research on software testing. One of the work that we know and is very related to search-based software testing, this workshop we are running today, is the work on ISTA, which was about the testing of or evolutionary testing of classes, which was for us a sort of a milestone for what is test case generation for Java classes. Of course, going forward or looking at the research going today is focused on machine learning based testing or dependability of machine learning based systems, automated testing for cyber-physical system, and of course the generic open problem of the testing oracle. So in this talk, deep learning testing, Paolo will try to tease you a bit with the challenges that are today of deep learning system and describe how they are different from system we have seen or have been testing in the past research. So thank you to have you here, Paolo. And maybe you can start sharing your camera and your screen with your presentation. And we are very excited to see you present this interesting talk, which I think will be quite well linked for the tutorial and follow-up panels. So we're really looking forward to it.
So thanks, Sebastiano, for the nice introduction. It's a pleasure for me to be here. So thanks for inviting me. Let me just fix a little problem I had with the screen sharing, because apparently I have to grant some permission through the Mac preferences.
Intentionally, no problem.
Any hint where I should do that? Well, let me try to press again the button, allow. No, maybe now it works. So you should see my screen now, right?
Yes, we see it.
Okay, very good. Great. So good morning, good afternoon, everyone. The title of my talk is Deep Learning Testing, and as mentioned by Sebastiano, what I'm presenting today is part of the results that were achieved in the pre-crime ERC project. It's a project devoted to testing unexpected execution conditions for general software, but in particular for software where unexpectedness is pretty important. And as I will try to convince you, this is the case definitely of deep learning systems and deep neural networks. So let me try to start with a brief introduction to deep neural networks. For those of you who are not familiar, but also to stress the differences with respect to traditional software. So a deep neural network is an arrangement of so-called neurons or artificial neurons, and these are computational units that are inspired to the biological neuron, which conceptually performs a very simple computation. It takes a number of inputs. Here you can see an arrangement of neurons. So if we pick one, this receives a bunch of inputs from neurons that are arranged in the previous layer, and that the computation done by each individual neuron is just a weighted sum of the inputs plus the application of typically a nonlinear function that produces the output, which is propagated then to the next layers. And this weighted sum is computed through a matrix of weights, which is the most important trainable parameter or set of parameters of a neural network. And actually, training a neural network amounts to exactly that, to finding optimal values for these parameters such that some loss, some error is minimized. So this, in a nutshell, is how a neural network operates. And in order to be able to train these parameters, what you need is typically a training set. You typically want also a validation set, which is used to test the generalization capabilities of the network. And then you come to the testing phase and you want to know how it performs. So great. So this is the idea of this computational model. It has been around for a lot of years. If we look at the implementation in terms of code, it's pretty simple, and I would say boring. It's a straight sequence of lines of code that create a model. Here is a sequential model. It creates layers, so it adds layers and layers, and then it compiles the model with some optimizer, and then it fits the data. So it computes the weights by fitting the data. So from the point of view of software development, it's pretty boring. But it's also pretty different from what we're used to. First of all, there is no control logic. So let's take the problem of a self-driving car. Let's assume the car has an input, an image from a camera, and has to predict a single output. Here, this neuron represents the single output that we are predicting, which is the steering angle of the car. While the input, here you see a number of inputs, not all of them. Each input is a pixel from the image. Good. So if we want to do this kind of prediction, then we will not implement any control logic such that if the curve is bending to the left, then increase the angle by that amount. You don't have anything like that. You just learn the association between the pixels in the image and the output from the training set. So there is basically no control logic. Everything is data-driven. Second important feature is that we don't have any notion of correctness. We will come back to this later. Neural network make predictions that have some error. It has some error in the training set and some residual error in the validation and in the test set, and they never have zero error. Zero error does not make much sense in domains such as image processing, where the input space is very complex. So it's even impossible to define the expected output for all the possible inputs. So we don't have this Boolean notion of correctness. Instead, we have a statistical notion, that is the notion of accuracy. So what is the proportion of images that are classified correctly, or mean squared error? What is on average the squared error in the steering angle prediction? And many things in the training process are non-deterministic. So at testing time, at prediction time, a neural network is completely deterministic. So if we give an image, it produces always the same steering angle for the same image. But at training time, the initialization of the weights is typically non-deterministic, and many optimizers that are used, like stochastic gradient, to compute the weights are also non-deterministic. So this means that if you train twice the same model, the same architecture, you get slightly different networks and models that behave slightly differently on the same test set. And this is pretty unique of neural networks. So why are we interested in neural networks? Well, because it's a recent success story. So in many research areas that were dominated by statistical techniques or other modeling techniques, deep neural networks have become the state of the art. They basically outperformed any other computational model. So if we take the example of natural language processing, then if we look at the past, we had many approaches based on hidden Markov chains that were sort of successful, but nowadays, if you wanna do machine translation or language modeling or dependency parsing or semantic row labeling, the best way to do it is by using a neural network to do it, which outperforms any hidden Markov model. And the same happened in computer vision. Kalman filters and all the kinds of filters developed in that field are outperformed by the neural networks in many tasks like image segmentation, object detection. Speech recognition is another example. Speech to text is nowadays done by neural networks. And programming, that's an interesting application area because we have seen very recently neural networks like Copilot that take a line of text that describes what we want to do and generate code, compilable code that most of the time is pretty usable and does the job. So that's another very interesting task where neural networks are becoming successful. And of course, since all these tasks are very complex, they open to the possibility of incredible applications, autonomous vehicles, medicine, and there's a number of areas where they are increasingly used. So deep neural networks have been around actually for many years. Why are they so successful now? And the answer is that they have become deeper, which trivially means they have larger size, they can count on more computational power and bigger data sets. And that is what made the power of the networks increase substantially in recent years. In particular, for software engineers, using a neural network and incorporating it into a system is more and more easy. There are frameworks like TensorFlow Keras or PyTorch that provide very nice and user-friendly interfaces. And whenever a system has to process complex data, so if it has to process natural language or images or has to do classification using feature vectors or predictions, then it makes sense to use a neural network for that task because that's the state of the art, which means that we are increasingly seeing traditional software being integrated and cooperating with neural networks, with components that are deep learning components. At the bottom of this slide, you see one example, which is self-driving car architecture, where we have some input from sensors, which is pre-processed by a standard traditional software component. Then for a couple of tasks like pedestrian recognition and lane keeping, so steering angle prediction, we use neural networks because these are the components that can do better this job. But then the integration is still a traditional software component. So in complex software systems that manipulate complex data, we have deep learning, deep neural network components and traditional software. But as I already mentioned, with a traditional software component, what we can stipulate is a traditional contract, which looks like this. If the input X satisfies the precondition and like it is greater than 0, then the output Y that we get from the computation satisfies another post condition, which is the square gives us X. And this is, of course, the contract that a square root function would stipulate with the users of this function. With deep learning component, it's completely different. The contract looks like this. The mean squared error on the test set is 0.01. So when predicting the steering angle, you have to expect in test mode this amount of error in the prediction. Or if you are solving a classification task like recognizing traffic signs or pedestrians, there's a level of accuracy in the task that is, let's say, promised by the contract, that is stipulated in the contract, but it's not 100%, it's not 1. So there is still a 5% probability that there will be a misprediction, a misclassification in the field. And this means that we need different ways to ensure quality and dependability when dealing with contracts that look like these ones and are no more Boolean contracts for which we have a clear, well-defined notion of correctness of the execution. So in recent years, if you look at the last, I would say 10, 15 years in software engineering, software testing conferences, there has been an exponential growth of techniques that deal with deep learning dependability and deep learning testing. And what researchers did was to take the traditional approaches, typically show that they cannot be applied as is. I will give you some examples in a moment to deep learning, to achieve deep learning testing, and they have adapted them. And this covers all the areas of software testing. So from test case generation to adequacy criteria, to mutation testing, to the Oracle problem, to data selection, test prioritization, security testing. Any sub area of software testing that you can imagine has seen one or more attempts to migrate it to deep learning component to see what we have to do when we apply similar notions to deep learning components. So in the rest of my talk, what I will do is I will present you a problem that is well defined, well known in traditional software testing, but is not so for deep learning components. Then I will briefly describe some of the solutions that have been presented in the state of the art in recent years, and I will conclude with what I call elephants. So in English, there's a way of saying, which is there's an elephant in the room, which means that there's a problem with something that everybody is aware of, but nobody wants to talk about. And today I will not talk only about solutions. Of course, we made progress, but I think the difficult problems, the difficult bits in this migration from traditional software testing to deep learning testing, the difficult bits, I think they are still there. And today I would like to discuss them with you and to point to them. So let's start with one problem, which is test adequacy. Test adequacy aims at answering a very simple question, which is, I mean, pretty important for developers. Have we tested the system under test enough? And if you take a traditional program like this one that computes the triangle type for a triangle with sides ABC, then we have a set of test cases that tests I don't know if something is not a triangle because it has a negative side, or if something is isosceles. Then we have this notion of coverage. So the simplest kind of coverage that we can consider in traditional software testing is statement coverage. And if we run these two tests here for this program, we will get this picture of coverage. Basically, 13 statements are executed, but 2 are missing. And the coverage is 87%, and these are the 2 missing statements, the ones that were not exercised by any test case. And of course, we know that we need more test cases because we want to test also what happens when we execute 11 or when we execute 13. So this notion is very well defined, it's very clear what you get if you apply these adequacy criterion and what you have to do to improve adequacy. Great. So let's now try to ask the same questions for deep learning systems. So have we tested the deep learning system enough? Let's take the steering angle predictor for self-driving car. So one possible test is this one. We take an image of a road, we predict a steering angle, and we get an angle, and then we say the prediction should be approximately, of course, this is a floating point, so it cannot be exactly, but approximately this should be 0.5 radians or degrees, I don't know the unit. Great, so we have a single test case, a single input, we run it. How much do we cover of the code, of the Python code that creates the neural network? Well, 100%, trivially, because there's no conditional logic, there's no branching, so there's nothing that requires specific input. At the same time, have we tested the system enough? I don't think so. So knowing that this test passes on a single image doesn't tell us anything about the capability of the neural networks to really drive a self-driving car. So clearly coverage in the sense of statement or branch coverage or traditional coverage is not enough for neural networks, and researchers have proposed a number of alternative adequacy criteria like neuron coverage, surprise adequacy, and mutation killing. Just to give you a quick idea about them, neuron coverage looks at the activation of all the neurons in the neural network. So this phi here is the output, the activation of a neuron for a given input. If this is above a threshold, the authors of this technique, of this adequacy criterion, say the neuron was activated, and basically we measure the proportion of neurons that are activated. And this is neuron coverage. And then you can be more fine-grained and you can say, okay, instead of looking at the output and the single threshold, we can look at the output and divide it into k beans. And then now we want to cover all the k beans for every neuron. And that's another notion of neuron coverage. It's called k multi-section neuron coverage. It was proposed a little bit later. And these were the first attempts to go beyond traditional coverage. Then, as I mentioned, there have been a lot of other works that proposed other adequacy criteria, but you got the idea. Basically, we have a neural network and we check how much of it was covered. Great. So what do we do in traditional software when coverage is not enough? Well, we add more tests because we want to test also the executions that were not tested before. What can we do with neural networks? Well, let's assume we have an initial coverage of 80%. We say that in terms of neuron coverage or surprise adequacy or whatever it is, that's not enough. We want to cover more, so we add more tests that increase coverage. Great. What do we do with these additional tests? If we train the network again using these additional inputs, then what could happen is that accuracy goes down because now we are focusing on corner cases that we don't want to be overrepresented in the neural network. So the puzzling bit or the elephant when we get to coverage for neural network is what to do with the coverage metrics, because adding more inputs is not necessarily a good idea if we want to predict or if we want to achieve a high accuracy in the field. So in general, the problem of knowing if and when it is beneficial to add inputs to the training set to get a better network is still completely unsolved. And having a given level of adequacy is not necessarily telling us that we need more inputs. Maybe this accuracy level is already the limit, and we have to expect 5% errors that cannot be improved. So adequacy is not currently is not currently a completely actionable criteria in deep learning testing. Developers of deep neural networks don't know exactly to do with a given level of coverage, and actually people have started to question neuron coverage or other coverage metrics for neural networks as a meaningful measure of how they work. So the general idea of migrating coverage is nice, but we are not yet there. There's still an elephant in the room that we have to address, I think. Second, software testing problem, test generation. So how do we generate test scenarios that are effective at exposing faults? In traditional software, there's a huge and incredibly vast literature on how to generate automatically or manually test scenarios, test cases. People did it randomly. People did it in a coverage-driven fashion. So coverage is driving what you generate in a diversity-driven way, in a mutation-driven. So we want to kill mutants with the generated tests, or in a black box way by covering the equivalence classes or the boundaries between classes. And all the idea behind all these different approaches to do test generation is that we have a goal, which is maximizing coverage in the second case here, or maximizing diversity. If we achieve our goal, then we are more likely to expose faults. That's the assumption of these techniques. In the panel in the afternoon, we will be talking about some of these techniques in particular for traditional software. Great. So as you can imagine, people migrated many of these ideas to test of deep learning components and came out with novel techniques to generate test scenarios, test inputs for neural networks. And here you see a non-exhaustive list of the approaches. Here really we had a lot. Adversarial examples was historically one of the first to generate inputs that are challenging for a neural network, but then we had generative networks. Of course, we have neuron coverage, so we can use it to drive test generation. Uncertainty is something we can measure for neural networks, and we can use it to generate inputs, surprise, mutation, and frontier. These are also concepts that can be used to support test generation for deep neural networks. Great, so let me quickly tell you something about a couple of these techniques, like the adversarial test generation. So in adversarial test generation, what people do is they take an input, then they find, like a traffic sign, they find the components, the elements in the input that are affecting the output to a major extent. And in this case, it's this pixel here and this pixel here. Then they manipulate these inputs to get a different outcome. So by changing these two pixels in this way, the traffic sign is no more recognized as a left turn, it's recognized as something else. Here, the green light, if you change this pixel, becomes a red light. So these are called adversarial example, and they are minimal changes to the input that produce a misbehavior. In generative adversarial networks, instead, people use the neural networks to move an input from one domain to another. For instance, we can take an image to be processed by a self-driving car taken in sunny conditions, and we can use a generative adversarial network, again, to introduce snow artificially into the image in a very realistic way. So the ones that you see here, they are images that were originally taken in sunny conditions, and then snow was added by a gun. And then people compared the prediction in the original and in the new condition, and if the two deviate, then by differential testing, they find something that might point to misbehavior. Great, so I gave you some ideas only of the first two families of approaches. These are really families because there are many techniques inside these big families. There's also other families, at least 5 more, with a lot of techniques. But you got the idea. Here the idea is how do we generate inputs that challenge, that produce misbehavior on neural network. And that's definitely useful. It's potentially quite important, but again, there's an elephant in the room, which is the validity or the realism of what we get. For instance, if we change an image of a road to an extent that it would be impossible even for a human to drive that road because the road is unrecognizable, is it still a valid input? Does it still make sense that the neural network, saying that the neural network is producing a misbehavior or a prediction that deviates a lot from the prediction in nominal conditions? So the problem of narrowing down the generated inputs to the valid ones, that are the ones that really matter because they are the ones that can be found in the field, is still an open problem. So people find a lot of inputs that potentially generate misbehaviors, but we don't know if these are actually relevant or valid. And a related question is that of realism, of naturalness. So if by valid, I mean something where a human can handle the input. So for instance, we have a traffic sign, it's valid if a human can tell what traffic sign it is. Good, but the second aspect is that of realism, of naturalness. So a traffic sign that has a couple of pixels properly chosen, manipulated, is definitely not realistic or not natural. It's not something that you can expect when driving in real conditions, in real roads, because of the way the pixels were chosen, because these are the ones that produce the maximum deviation in the output. So that can happen if we have an attacker attacking the deep neural network. Then, of course, the attacker can manipulate intentionally those pixels to get a misbehavior. But it's very, very, very unlikely that we see this in reality, in natural conditions. So again, that's an aspect that is not considered very much, and adversarial examples are very useful definitely for security testing of a neural network, but if we want to know the dependability in the field, I don't think they are the best technique to use. Great. Mutation testing and mutation analysis is another technique that is widely used with traditional software, and one of the first works that proposed a mutation for deep learning component is Deep Mutation++. It was proposed in 2019 at AEC. And it is pretty simple. We have a neural network that is basically a collection of weights, represented here as the connections between neurons, and we change one or more to another value, and we get a mutant. And if the output of the original network differs from the output of the mutant by more than some threshold, then the mutant is killed by the input X. If no input X can do this, so no input can produce a different output, then the mutant is unkilled, and we need more inputs to be able to kill it. That's how the traditional mutation analysis idea has been migrated, I would say, to deep neural networks and deep learning testing. Great. So one of the issue behind this approach is that this test here is completely deterministic. So we have one output of the model, one output for the mutant, but in reality, if we train the model twice or the mutant twice, we get different outputs. So we cannot, we might, in this equation here, we might replace m prime, the mutant, with m. So we can have m trained the first time minus m trained the second time, and still the difference could be higher than some threshold, which means nothing. It just means that the training process is non-deterministic. So this non-determinism is quite important when we are making reasonings, when we are analyzing the output of a neural network, and we cannot just treat it as a traditional deterministic output. We have to take into account the non-deterministic behavior that is associated with training and multiple trainings. Second elephant is the so-called coupling effect. So one of the reasons why mutation testing is so popular is because people believe that the coupling effect holds, which means that defects introduced artificially through mutations are representative of real faults. And if we have a test suite, a set of test cases that can expose the artificial faults injected through mutants, then that test suite is effective also at exposing the real faults that can affect the real system, not the mutant. So this is called the coupling effect. And when we are changing individual weights in a neural network, so we are picking some of them and changing their value, here there's no insurance of the coupling effect. So how do we know that this change here is coupled with a fault, that a real fault that a deep neural network developer would or might introduce in neural network? And this is a big elephant. So it's great to have these mutation analysis and mutation testing tools, but we have to go beyond that. And I think questioning the coupling effect and investigating it is quite important for the future. Test oracle, that's another big issue, big problem in traditional software testing. If we have a program that computes the triangle type, we have the specs that define formally the different triangle types. Then when we have a test case, like the invocation of triangle type with 2 to 3, we know what to expect. Here we would expect isosceles. In that case, the execution is correct, otherwise it is not. Great. What's a test oracle for a deep neural network? Well, we can say that for a given input that represents a handwritten digit 0, the output expected is 0. For a given image of a road, the angle should be 0.5 with at most some error, but here again there's an elephant. If we just look at the output and the accuracy of the output for individual predictions, we know we don't know much, or we don't have, let's say, complete knowledge of what to expect at the system level. So we might have inaccurate predictions on individual inputs that are compensated if we by the overall system. So we can have individual errors that might violate this assertion and accumulate and are compensated at the system level, and there is no misbehavior of the system. Or the other way around, we might have little errors below the threshold that we check in these assertions, but they accumulate and they lead to a system level failure. So we cannot have oracles that talk only about individual predictions at the unit level, at the level of the individual neural network. We need some way to reason on the misbehaviors of the entire system. And there's an interesting paper presented at ICST 2020 that compared offline, which means single predictions like these ones, to online testing, which means testing when the neural network is operating in the field, like in a self-driving car. The other important area where there's a bit of research, especially in the AI field, in artificial intelligence and machine learning, more than in software engineering and software testing, is about understanding the conditions of misbehaviors. So here it would be quite important to report, when we do deep learning testing, to report to developers inputs that trigger misbehaviors, but also to point to the reasons why we have misbehaviors, so to the features of the inputs that produce a misbehavior. And there's an area of AI that is called explainable AI that goes in this direction, because they look at the inputs and they try to find the reasons why we have a given prediction, a given behavior of a neural network. And here you can see some examples of these explanations. So the reason why a given digit was predicted to be a 0 is because of these pixels. So these are the pixels that are, the light pixels are the ones that are most responsible for the prediction of a digit being a 0 or being a 1 and so on. So with these explainable AI maps or heat maps, we can understand what are the parts of the inputs where the attention of the neural network is mostly focused. But this does not necessarily point to features of the inputs. So here I think we are still far from an interpretability or an understandability of the misbehaving inputs that is really actionable for developers. Because from this low-level information about the pixels that are responsible for a prediction, we don't know in what ways we should improve the neural networks or the training set, or we should improve the test set for the neural network. So to summarize, in the talk I presented 6 elephants, 6 areas of future investigation where I think the existing literature made some progress, but now is sort of hitting a wall, and we need a way to jump over the wall, to go beyond the problems that we found. And one is test adequacy. So how do we know if improving adequacy is effective in the field? Test generation, how do we know about validity and realism? Mutation analysis, we have the non-determinism problem and the coupling effect problem. Test oracle, where we want to reason at the system level and understanding how do we know the input features that make a system misbehave. So these are big problems. They are non-trivial ones. I think they are the ones that typically in the initial phase of migrating from traditional to deep learning testing, people sort of ignored or didn't consider in depth, but that's to me where the future research should go. And in our pre-crime European project, we did something in that direction. So now in the final part of my talk, I would like to tell you about some recent results that we obtained that go in the direction of addressing partially, not all of them, but some of the elephants. Of course, these elephants are difficult to deal with. I think they will require more research than, I mean, the initial one that migrated the traditional software testing techniques to deep learning, but they are also very challenging, very interesting research directions. So about validity, what we did in pre-crime was to develop a technique for test input generation that is based on the notion of frontier. So we don't want to generate, here you can see the input is a digit for a classifier of handwritten digits. We don't want to generate a digit that is very far from the inputs that are classified correctly, something that is misclassified, but just because it doesn't look really like a 5 or any realistic digit. So to achieve this goal, we introduced the notion of frontier. A frontier is a pair of inputs that are very close to each other, like these two, but on one of them, the network behaves correctly, on the other one, it misbehaves. This is classified as a 5. So the hope is that if we are at the frontier, then we have more chances to produce valid, realistic natural inputs. And then, of course, to know how we performed, we did a human study. So we asked about the validity of the inputs to humans through questionnaires. And what we found is that first, our technique generates a lot of valid inputs, which is good. And second, we found that, as expected, this depends on the quality of the neural network under test. If a neural network is low quality, the blue one, then it's easier to stay in the validity domain and generate frontier inputs. But if a neural network is high quality, like the orange one, that's more challenging, and of course that's expected. So if you really want to generate a misbehaving input, you have to go probably beyond the validity domain, which is something that we conjecture from the beginning. In the area of mutation analysis, we have introduced the notion of mutation killing that is non-deterministic, that is statistical, to take into account what I briefly described before. If we have an original program, an original neural network P, and we train it 100 times, each time we measure the accuracy on the test set, we will get a slightly different value. Here, the median accuracy is something like 75%, but there's some spread between 70 and 80% with some scattering of the distribution. If we do the same for the mutant, train it multiple times, measure accuracy, the accuracy is distributed like this. So how do we know if the test that we are using is enough to discriminate the mutant from the original program? We cannot just do a single run and compare accuracy, because we might get exactly the same accuracy. That does not mean that the test suite is not able to discriminate. It might just be due to chance. So to take into account the statistical distribution of accuracy, what we do is we propose to apply a statistical test like Wilcoxon to compute a p-value that tells us the probability of a type 1 error, basically the probability of an error when we reject the null hypothesis. Rejecting the null hypothesis for us means that the two distributions are different, which means the mutant is killed because the accuracy has dropped on the mutant. So in order to be able to reject the null hypothesis, what we require in our is killed mutation killing criterion is that the p-value is small, so we minimize the chances of a type 1 error, and that the effect size is non-negligible. If this happens, then we can reliably, from a statistical point of view, say that the mutant is killed, and this was presented at ICST in 2020. To go in the direction of ensuring that the coupling effect is valid, holds, we developed our own mutation analysis tool for deep neural networks, which is called DeepPrime. In turn, this tool is based on a previous work that we did, which was the construction of a taxonomy of free of faults for deep learning components. And DeepPrime is not really mutating individual weights of a neural network. It's not picking a weight and changing it. What it is doing, it is simulating the process of introducing a real fault that we have observed in the field with real developers. So for instance, it takes the training set and it makes it unbalanced, because unbalancing of the training set is one of the real problems that developers encounter when training neural networks. Or looking at the architecture. Deep crime can make the architecture suboptimal by dropping some layers, or looking at the hyperparameters, it can change the learning rate to make it inaccurate. And all these are based on real faults. So in this way, we get a mutant that has more chances, that is more likely to satisfy the coupling effect, to really be coupled with real faults. Of course, we have not shown yet with this work that the coupling effect holds. Actually, even for traditional software, there's no final answer to this big question. So I expect that even in deep learning testing, it will take quite some time to get even some attempts of answering the overall question, which is a big one in my opinion. But with deep crime, we are simulating real faults in a neural network, and this approach was presented last year at ISTA. About the test oracle, so we said that the oracle that we have are at the component level, at the deep neural network level, which do not necessarily correlate with system level failures. So in a work that we presented at SBST last year, we proposed a set of quality metrics and oracles, in particular for self-driving cars. So when you have a model like Dave2 or Chauffeur or Epoch, these are examples of neural networks that are widely used, architectures that are widely used for self-driving. You can observe different driving styles. Here in particular, the green and the red are under different conditions. But in general, even if you compare different models, you see different styles. So what is a good or a bad quality of driving? And in this work, we investigated a number of metrics that have been proposed to assess the quality of human driving under various conditions, especially when the quality of driving deteriorates, like under the effect of alcohol. And we have checked the validity of these metrics and proposed new ones for self-driving cars. And here you can see some. So standard deviation of the brake level is one metric that tells you a lot about the quality of driving for a self-driving car, the standard deviation of the lateral position. And we had a bunch that have been proposed going in the direction of having oracles that work at the system level. I talked about understanding and explainable AI, which potentially is very important, because when we get a misbehaving input, we also want to know why the neural network is misbehaving for a given input. But as we have seen, knowing at a low level that a particular pixel is responsible for a misbehavior is not particularly useful or informative for developers. Good. So in our ISTA 2021 work, Deep Hyperion, we proposed to use human understandable, interpretable, high-level features. If we have a digit to be recognized, a handwritten digit, the orientation of the digit, where it is tilted on the right or on the left, it's a clearly understandable feature. The luminosity is another easily understandable feature. If we have a self-driving car, the minimum radius of the curve or the mean lateral position, these are pretty clear and pretty understandable features. So we have defined feature maps that take inputs and map them to an understandable and interpretable feature. We have produced a test generator called Deep Hyperion that can populate a feature map like this one or this one. And this tool is also trying to expose misbehaviors in each cell of the map. So the cells that have a bold contour are ones where we have misbehaviors. And sometimes having a particular region of the map with misbehaviors can be interpreted in a very discriminative way. So if you want a misbehavior, if you want to expose a misbehavior for the driving model that we are testing, the conditions that we have to achieve is a curve with a mean radius in this range, and we have to be able to generate a behavior of the car with a given mean lateral position. So these are definitely more interpretable. I'm not saying that we solved the problem. Of course, the problem of understandability of the inputs that are generated by automated test generators and automated and interpretability of the inputs that are generated automatically is still an open problem, but this goes in the direction of improving the interpretability and making automatically generated inputs more interpretable. So with this, I think I'm at the end of my talk. This slide is just showing you again the elephants, because now I want, of course, to hear your opinion about the elephants, your questions, your comments. I'm very curious about your reaction to my talk.
Well, congratulations, great keynote.
Indeed. So I think while we are waiting for question on the chat, maybe I will try to open so that maybe people can jump on the conversation. During the keynote, Paolo, you mentioned a lot of problems. Actually, I think open problem about level of realism, of explainability of AI-based system, and you talked a lot, especially in the last part, on certainty of an environment. But you also know that AI-based system have the problem on non-determinism. You give the same inputs and probably would be a non-deterministic behavior, even though you have an environment that has, for some reason, the same conditions. So here the question, do you consider we should be considered to address the problem of non-determinism in a specific sense? Do you think that humans should be considered in the loop in some way, just in a broader sense?
Yeah, thanks, Sebastian. It's a very interesting question, an important aspect that I didn't touch, because I talked about the non-determinism of the training process, which is one source of non-determinism, which is very often overlooked by researchers. But you're right, there's another source of non-determinism, which is the environment where these systems operate, because typically they are operating in very complex environments. If we have a self-driving car or a drone, I mean, any simulator, or I mean, if we are in the real world, that's even worse. You cannot have exactly the same conditions. All the simulators, to produce realistic effects like the wind or the light, they have some non-deterministic behavior, and if you run the same test twice, you get slightly different outcome, which means that we have at least two sources of main sources of non-determinism. One is the training process, but the other can be also the environment, especially if you have a complex environment. So what can we do about it? Well, we have to randomize, of course, across both sources of non-determinism, but this comes with a big problem because it takes a lot of time. So if we are talking about a simulator, it means that we have to run, just to get a single answer, like a single level of accuracy, we have to run the simulator a lot of times. So I think that's another important direction of future research, which is how can we optimize the executions of tests in environments that are non-deterministic, to be able to still get valid results. Otherwise, really, we have to allocate clusters and days of computing time to be able to get any answer for the techniques that we want to develop. So yeah, you're right. That's another big problem that we have.
No, but I mean, you were very comprehensive. So I was just curious, to have your thought on that part, that I think you are for sure not overlooking, you're for sure focusing, but I was curious to hear from you. I don't know if Giovanni, you had a question also from your side. I will have another, but probably, Giovanni, you have maybe come from your side, and there will have maybe other from the audience.
Well, thanks for the great keynote, Paolo. Very insightful. And my question is more like a provocative one. What would you consider a bug in a deep learning system? Would you consider a misclassification as a bug? Or how? I saw many discussions about it in other papers as well, and I want to know your opinion on that.
Yeah, that's a very good question. It's another elephant that I touched only marginally, but it's a very important one. So of course, for researchers, it's the simplest choice of definition is misclassification is a bug. Because then you can count, it's easy, you can propose a new technique, you count the new misclassifications, and you are done. But that's not the end of the story, because To me, a bug is something that affects the development process. It's a mistake in a way done by developers in the process. And when we have built the taxonomy of real faults that was the basis for deep crime, we looked into the way developers of deep learning components can make mistakes. We looked at different sources. We mined GitHub and extracted the different comments on the issues that are traced there. We looked at Stack Overflow and the faults that people report there and ask questions about. We also interviewed a number of developers who are active in the construction of deep learning systems and components, and we collected a taxonomy of faults that affect deep learning developments. And these faults are, I mentioned some of them, and they are sort of implemented in deep crime. They affect typically either the training process, so they can affect the training data. So you have a bug if the training data is unbalanced, if a class is underrepresented, or if some conditions are underrepresented. They can affect the architecture of the neural network that you're using, because some layers that are quite important to extract some features are missing, or they are not sized properly. They might affect hyperparameters. The learning rate might not be properly set. So there's a number of bugs, and these are the faults. So if we are talking of what is a fault is something like this. The learning rate is set wrong, or the training data misses some particular kind of input. Then a symptom of this could be a misclassification, but when I talked about contracts, misclassifications are always there. If you have 95% accuracy or even 99% accuracy, 1% is still misclassified. So discovering one more or even 100 more misclassifications is not really telling you that you have a bug unless you can, let's say, connect this misclassification to something that was done wrong in the training process. So some classes that are missing, that are important to be added, or some hyperparameter that was set wrong, some architectural choice that was wrong. And of course, making this connection is way more difficult than counting misclassifications. So everybody does the latter, but you're right, it's a big elephant. The other aspect is that we don't have a repository. So in traditional software, we also are missing repositories, but at least we have things like defects4j. So we have well-documented bugs that we know where they are, and when we create new tests, we know if these bugs are exposed or not. We would need something similar for deep learning components, because then we could say this input generation technique is able to expose a real bug, something that was done wrong for real in the development process of a neural network, not really something that is just misclassified.
I see.
So thanks, it's a very good comment.
Thank you, very clarifying, by the way.
Question on the chat, Paolo. I don't know if you noticed, how does the traditional mutation analysis compare to deep learning specific mutation analysis, the leading statement or an expression? I think it's quite it's an interesting question. It's in the chat, Paolo. You can also read it.
Yes, I've seen that. That's also interesting. I mentioned in my talk a work that we presented at ICST in which we investigated empirically existing tools for mutation analysis of deep learning components. We focused on, in my talk, I focused on the notion of mutation killing because it's quite important to make it statistical. But we also investigated this aspect, which is what if you apply traditional, let's say, mutation techniques and like deleting statements or expressions. And what you get is that the symptoms, the effects of these changes are typically much more visible. They either make the network no more compilable, or the training process fails with some exception, or you corrupt the shape of the input. So you can still do that. You can still inject traditional faults and find maybe something interesting, but it's a completely different category of faults. You cannot expect, so for instance, if your training data is unbalanced it's definitely impossible to see this by changing randomly some statement in the program that creates the network and trains it. So let's say traditional mutation analysis remains important, especially because these libraries like Keras or PyTorch are complex, so it's possible to misuse them. It's possible to introduce bugs in a way they are integrated in the system, but the two kinds of faults are quite disjoint from each other. So if you want to discover the faults that are specific to the training process of neural networks, then you need specific mutation operators.
I think I would add another question. I think there's still time. You mentioned, Paolo, during the talk about understandability or explainability of AI, and I usually associate it, maybe I'm wrong, on trustability of AI. So if you go, whether with researcher or practitioner, you want to make sure that this an AI system is trustable. It's a very difficult problem, but at least if you're able to make it explainable, we can find out what is wrong in it. So here, just to mention an example that you referred in the beginning of the talk, Copilot. Now you can create from text code, but there are also recent results that demonstrated that generating code from open source projects can generate unsecure code. So here, when using AI, it's very sensitive to the data. So what we should do or consider or should not do when using AI, or if you want, or what we should do for ensure reliability or testability of such system. It's a bit broad topic, but I wanted a bit.
Yeah, no, I think that's very interesting. It's really looking deep ahead in the future because we are not yet there. Unfortunately, I mean, we are still the ones who program, and it's not an AI who programs instead of us. But looking at the example of Copilot, it's not a science fiction future. It's something that is increasingly, adopted. I know that developers, real developers, are trying to use Copilot sometimes they just to see what they get, and sometimes they get something useful and they use it. They change it a bit and they use it. So probably this has the potential to revolutionize the way we develop software. And as you said, being a software engineer maybe will mean testing the software that an AI produces, or testing the trustability or security testing, what it does. I don't know. I don't have an answer, but it's really fascinating to think of what could become software testing, software engineering in this future where AI create software or create code with us or instead of us.
Great. I think we are reaching sort of the end of this amazing keynote. I think the question and answer was very exhaustive. Thank you, Paolo, really, for exhaustive talk and engaging with all answer very exhaustively. I think we will have quite a few minutes of break after that, so will be a fresh energy for the next section. So let's thank everyone for what's joining here, Paolo again, and we see you in a few minutes after the break. It should be 15 minutes or so.